This is Steel Shorts with the American Institute of Steel Construction. Quick stories about the integration of architecture and steel structure.
Hi, I'm Kyle Ingber. I'm a design architect for HOK based in Chicago, and I was the project designer for O'Hare's Terminal 5 East Expansion.
And hi, I'm Mark Hendel. I'm the engineering practice leader from HOK's New York office, and I was the lead structural engineer for the O'Hare Terminal 5 expansion.
For the O'Hare International Terminal 5 expansion, we wanted to create a rare experience of rest and pause for passengers in a building designed for movement. It is more of an open plaza with a market versus a street or corridor.
The Terminal 5 East expansion added to the existing building from the early 1990s. Early design iterations of the space called for an expanded bar that added to the axis of the existing building, and through a series of design iterations, the design team ended up on this bent L-shape or boomerang shape to the plan. This ultimately created a central space that allowed for the largest volume and natural light within the central area where passengers would be gathering. As we developed the plan, this central area of the boomerang shape also became the space of the highest volumes that we allowed for the most natural and artificial light to come into the space as passengers are gathering. Ultimately, this space is going to be where most passengers are either entering the country or leaving the country, so it's going to be the first or last thing they see, and we wanted to make sure that there was a really significant focus on natural light, volume, and creating a human scale for the space. Throughout the design process, the design architects collaborated very closely with Mark and his team, the structural engineers, from the beginning of the design all the way to construction. To create this volume and light in the central space, we started with a flat roof and ceiling and peeled it down the center to create a high roof and low roof element, where the resulting space was a clear story window that ultimately allowed for natural light to come into this space. This is further amplified by complete perimeter glazing that allows for views out to the airfield and maximum transparency. This was ultimately in conjunction with the lighting elements that were in the space to create the maximum overall light and volume within the central marketplace area.
Structurally, the East Concourse extension structure consists of a deep foundation and slab-on-grade level supporting a structural steel frame above. The concourse level consists of a composite concrete slab-on-metal deck supported by steel wide-flange beams and columns. The structural steel roof is divided into a planar lower roof and a sloping and curving upper roof with a clear story between the two roof surfaces. Both roof surfaces are comprised of metal deck on steel wide-flange beams and columns. Above the concourse level, there are very few interior columns to keep views unobstructed and maximize the flexibility of the space.
As we began the design of the project, some of the initial studies looked at a more faceted approach to handling this boomerang shape of the plan. As the design advanced, we started to realize that a singular parabolic curved form would be the best way to tie the whole space together in a really simple and elegant way. So in order to advance the design team for the architecture side was able to share some of our three-dimensional models, specifically in the software Rhino, with the structural design team.
The initial roof concept developed by the architectural team presented the structural team with a few challenges. How do we take a doubly curved and tapering surface generated in Rhino and make it definable and constructible? In order to achieve this, the structural team developed a parametric definition of the mass that rationalized the mass into a series of planar and single degree of curvature surfaces which closely approximated the desired form, all while verifying that the resulting form met the minimum necessary roof slopes and didn't obstruct the line of sight from the ramp control tower. Once we had the basic definition in Grasshopper, the architectural and structural teams were able to sit together and play with the parameters to arrive at the final roof geometry that we see here today. The main structural challenge of the roof form is the clear story, which passes diagonally across the concourse as it advances along. There were a few different ways to support this. Ideally, with a clear story, you would like to put columns that support both the lower and upper roof elements. However, in this scenario, a row of columns at every grid line would create a visual wall right across the concourse, which was unacceptable architecturally. So that was out. Another option considered by the design team was to introduce a truss along the clear story. However, given the lack of interior columns, the truss span became so long as to become untenable. Additionally, with the truss option, the introduction of diagonals for the truss created further obstruction to the clear story, reducing the light that was entering the space. Instead, the design team decided to take advantage of the geometric flexibility of steel and use a series of continuous bent girders that span across the open space of the concourse. The bent girders consist of a wide flange beam that's been cut on an angle and rewelded to form the bent portions. The member size is continuous along the length. Given this simple approach, which is relatively straightforward for steel, the location, length, and angle of the bend could be varied from grid to grid without adding significant fabrication challenges. The location and depth of the bends and the girders increases as the clerestory expands and shifts towards the central marketplace where the clerestory and roof reach their peak. After arriving at the bent girder concept, the structural team and architectural team examined several angles for the specific bend in the girder. Initially, we did look at running the bent portion of the girder vertical. However, this created issues structurally as it resulted in stress concentrations at the peak of the bend in the wide flange member.
Architecturally, it presented us with some opportunities from a design perspective, though, as the bend of the girders allowed the clerestory to be more fluid and continuous as a singular expression. And the angle of the bent girders also helps to reinforce the parabolic continuous geometry of the space.
The resulting angle allows the girder to be expressed in the space. It becomes a sculptural element. In addition to supporting gravity loads, the bent girders also create a diaphragm connection linking the lower and the upper roof portions. Documentation of the sloping and curving roof geometry was a challenge which the design team used Grasshopper to address. As noted, in addition to defining the roof surface geometry, the Grasshopper script also produced the steel geometry considering the necessary steel offsets to accommodate deck support bent plates. Using this geometry, the script produced a table of control point elevations and dimensions for each bent girder, which was included on the drawings. The bent girder control points table was used by the detailer to set out the roof structure. Structural steel was the natural choice for the roof structure, given the long spans, up to 87 feet clear in the central marketplace, and the desire to keep the roof geometry as shallow and planar as possible. The entire roof structure is comprised of standard rolled wide flange shapes.
As Mark mentioned earlier, the exterior and roof form is made up of simple, planar, and barrel vaulted forms so that we could optimize the ease of constructability for exterior surfaces. On the interior of the space, we decided to utilize that geometry as a singular expression with a lofted surface that continues from one end of the extension to the other. In order to address a human scale element to the ceiling, the design team looked at a series of iterations and landed on these domes, over 400 of them, that occupy the ceiling to create a human scale. They add artificial light, diffuse light, and direct light from downlights that are adjacent to each of these domes. The geometry of the domes follows the parabolic arc of the overall geometry and allows to reinforce the geometry of the roof, the ceiling, and the clerestory. These domes were also created using Grasshopper. That allowed the design team several efficiencies. It allowed us to iterate different locations and sizes of the domes and their placement. It allowed us to ensure that the slope of each of the domes was relative to the slope of the ceiling at that moment. And it allowed us to create three-dimensional points for each of the domes to allow for constructability. The O'Hare Terminal 5 East expansion and its design was ultimately completed through a close collaboration between the design architects, the structural engineers, our contractor, Austin Power Partners, and the steel fabricator, Lejeune.
The design team utilized new tools to arrive at a complex design that is elegant and sculptural and constructible. By doing so, the team was able to revitalize, modernize, and expand a 30-year-old terminal for years of use to come.
For more information for students on a steel cheat sheet, scholarships, competitions, and more, see aisc.org/archeducation.